On the morning of September 15, 2017, at exactly 7:55 a.m. Eastern Time, one of humanity's greatest robotic explorers reached the end of its journey. After spending nearly 20 years traveling through space, including 13 years orbiting Saturn, NASA's Cassini spacecraft made its final descent into the giant planet's atmosphere. This was not a malfunction. It was intentional. Running dangerously low on fuel, Cassini was given one last command: dive directly into Saturn at more than 113,000 kilometers per hour. As it plunged deeper into the atmosphere, the pressure and heat rapidly became overwhelming. Within moments, the spacecraft was torn apart by aerodynamic forces and vaporized completely, becoming part of the very planet it had dedicated its mission to studying. Nearly an hour later, the final radio signal reached Earth. At NASA's Jet Propulsion Laboratory, many of the scientists and engineers who had spent decades working on the mission openly broke down in tears as Cassini's transmission disappeared forever. But the most remarkable part of Cassini's ending is why NASA chose to destroy it in the first place. By the final years of the mission, Cassini had made discoveries so important that they fundamentally changed how scientists viewed Saturn's moons. Beneath the frozen surfaces of worlds like Enceladus and Titan, the spacecraft uncovered evidence of active geological activity, environments that appeared far more dynamic and potentially far more habitable than anyone had expected. In one case, Cassini detected conditions that astrobiologists considered genuinely capable of supporting life. And that created a serious problem. Once Cassini ran out of fuel, NASA would lose the ability to control it. Eventually, the spacecraft could have drifted unpredictably and crashed into one of those moons. If even tiny amounts of Earth bacteria survived on board, they could contaminate environments that scientists believe may contain the ingredients necessary for alien life. NASA could not take that risk. Cassini was sacrificed to protect worlds that might already be biologically important. That decision alone reveals just how seriously the scientific community viewed what the mission had uncovered. Because Cassini didn't simply study Saturn, it transformed our understanding of where life might exist in the solar system. And its final moments became just as scientifically meaningful as the discoveries that came before them. Cassini began its journey on October 15, 1997, launching from Cape Canaveral aboard a Titan IVB Centaur rocket. But the spacecraft was not traveling to Saturn alone. Mounted to Cassini's side was another spacecraft entirely, the European Space Agency's Huygens probe. Unlike Cassini, which was built for years of orbital science around Saturn, Huygens had one specific mission. After arrival, it would detach, descend through the thick atmosphere of Saturn's moon Titan, and send back as much information as possible before its batteries died on the surface. Together, the Cassini-Huygens mission became the most massive interplanetary spacecraft NASA had ever launched at the time. Fully fueled, it weighed over 5,700 kilograms, heavier than a fully loaded transit van. Reaching Saturn, however, was far more complicated than simply pointing the spacecraft outward and accelerating. The journey took 7 years and required an intricate sequence of gravity assists across the inner solar system. Cassini flew past Venus twice, then Earth, then Jupiter. Each encounter used the gravity and orbital motion of the planets themselves to redirect and accelerate the spacecraft without consuming large amounts of fuel. It was an extraordinarily precise maneuvering strategy. A small navigational error during any one of those flybys could have thrown the entire mission off course. By the time Cassini reached Jupiter in late 2000 for its final gravity assist, it had gained enough velocity to continue onward towards Saturn. Then, on July 1, 2004, came the most dangerous moment of the entire mission. As Cassini approached Saturn, it fired its main engine for 96 uninterrupted minutes in order to slow itself down. Without that burn, the spacecraft would have flown straight past Saturn forever, disappearing into deep space and ending the mission instantly. Everything depended on that engine firing correctly. It worked. Cassini successfully entered orbit around Saturn, becoming the first spacecraft ever designed to spend years exploring the ringed planet and its moons from within the system itself. Originally, the mission was expected to last only 4 years. Instead, the science coming back from Saturn proved so extraordinary that NASA extended the mission once, and then extended it again. What began as a 4-year exploration ultimately became a 13-year scientific campaign. By the end of the mission, Cassini had completed 294 orbits around Saturn and performed 162 close flybys of its moons. It transmitted more than 450,000 images back to Earth and gathered enough data to generate thousands of scientific studies. No previous mission to the outer solar system had ever produced information on that scale. Every extension of the mission had one purpose: continue gathering data as long as the spacecraft remained operational. And when fuel reserves finally began running critically low, NASA approved one final phase known as the Grand Finale, a series of daring maneuvers designed to extract as much science as possible before Cassini's inevitable destruction. When Cassini arrived at Saturn, Titan was already one of the most anticipated targets in planetary science. It was the only moon in the solar system known to have a thick atmosphere, nitrogen-rich, like Earth's, but roughly 4 times denser at the surface and laced with organic compounds, including methane and ethane. Its surface had never been directly observed because the atmosphere was packed to visible light. Voyager 1 had flown past in 1980 and seen nothing but a featureless orange haze. What lay beneath was entirely unknown. On January 14, 2005, the Huygens probe answered that question. After separating from Cassini on Christmas Day 2004, Huygens fell through Titan's atmosphere for 2 hours and 27 minutes, transmitting data and images throughout its descent. What the cameras revealed was a landscape of breathtaking familiarity. River channels carved by flowing liquid, a flat, dark plain at the landing site that appeared to be a dry lakebed or sea floor, and rounded pebbles of water ice, smoothed by erosion, just as river stones on Earth are smoothed by water, scattered across the surface. Huygens had landed on a world shaped by fluid dynamics, weather, and geological processes recognizably similar to Earth's, but operating at -179 degrees Celsius with methane in place of water. Over the following years, Cassini's radar instrument, which could penetrate Titan's opaque atmosphere where cameras could not, mapped the moon's surface in extraordinary detail. It found lakes, not metaphorical lakes or dried lake beds, actual, current, liquid-filled bodies sitting on the surface, dark and still, the largest of them, Kraken Mare, covering an area larger than the Caspian Sea. It found river deltas, where liquid had carved channels and deposited sediment into the lakes. Seasonal changes in the distribution of surface liquids, consistent with a methane rainfall cycle, and dune fields of organic material blown into linear ridges by the moon's sluggish winds. Titan has weather, it has seasons, it has a hydrological cycle. The working fluid is methane rather than water, and the temperatures are incompatible with life as we understand it. But the processes, evaporation, precipitation, erosion, sedimentation, are the same ones that shape the surface of early Earth. What Titan demonstrated with a clarity that no previous observation had approached is that planetary chemistry does not require proximity to the Sun. Complex, organic chemistry, liquid-driven geology, and dynamic atmospheres can exist at Saturn's distance, and, by extension, at the distance of any planet in any solar system orbiting any star. Titan expanded the definition of where interesting chemistry can happen. If Titan was the moon scientists were most excited to explore before Cassini arrived, Enceladus became the discovery that changed everything. Before the mission, Enceladus barely attracted serious attention. It's a relatively small moon, only about 500 kilometers across, orbiting deep within Saturn's ring system. Bright, icy, and heavily reflective, it was generally assumed to be frozen solid and geologically inactive. Just another cold object in the outer solar system. At the time, few scientists expected it to become one of the most important worlds ever studied. Then Cassini arrived. In 2005, the spacecraft detected something astonishing near Enceladus's south pole. Enormous plumes erupting directly out of the moon's icy surface. These were massive jets of water vapor, ice particles, and gas, blasting hundreds of kilometers into space through deep fractures in the crust. Those fractures would later become known as the Tiger stripes. Nothing like it had ever been observed this far from the Sun. Enceladus was not frozen and inactive. It was alive with geological activity. Material from deep inside the moon was continuously escaping into space, feeding Saturn's faint E-ring with fresh ice particles. What scientists initially expected to be a quick flyby target suddenly became one of the highest scientific priorities of the entire mission. Over the next decade, Cassini repeatedly returned to Enceladus for closer and closer encounters. Some flybys brought the spacecraft within just 25 kilometers of the surface. During several of those passes, Cassini flew directly through the plumes themselves, allowing onboard instruments to literally sample material erupting from the moon's interior. What the spacecraft found was extraordinary. The plumes were not made of simple water vapor alone. Cassini detected sodium chloride, essentially salt, strongly suggesting that the water inside Enceladus had been interacting with rock for long periods of time, much like Earth's oceans interact with the seafloor. Then came another discovery. The spacecraft identified tiny silica particles that form under extremely specific conditions, hot water reacting with rock at high temperatures. On Earth, this kind of chemistry is associated with hydrothermal vents, environments where superheated water rises from beneath the ocean floor. Cassini also found complex organic molecules within the plumes. These included large carbon-based compounds considered important building blocks for biological chemistry. And perhaps most importantly, the spacecraft detected molecular hydrogen. That matters because hydrogen can serve as an energy source for microbial life. On Earth, entire ecosystems exist around deep-sea hydrothermal vents where organisms survive completely independent of sunlight, using chemical reactions instead. The process believed to produce this hydrogen on Enceladus is known as serpentinization, hot water reacting chemically with rock beneath the ocean floor. Taken together, Cassini's discoveries revealed something remarkable hiding beneath the moon's frozen crust. Enceladus possesses a global subsurface ocean, an ocean of liquid water trapped beneath ice, resting above a rocky seafloor containing chemical energy, organic compounds, and the minerals associated with long-term water-rock interaction. In other words, Enceladus appears to contain all of the major ingredients considered necessary for life. And on Earth, wherever those conditions exist together, life exists. Every known hydrothermal vent system on our planet, no matter how dark, isolated, or extreme, supports living ecosystems. Enceladus may have maintained similar conditions for billions of years. That does not prove life exists there, but it means that one of the best environments for life beyond Earth was discovered in a place almost nobody expected to matter when the mission first began. And that realization fundamentally changed planetary science forever. Alongside its moon discoveries, Cassini fundamentally revised our understanding of Saturn as a planet. Its imaging system captured the atmosphere in detail that no previous telescope or spacecraft had matched. And what it showed was a world of extraordinary dynamical complexity. Saturn's atmosphere is organized into bands of alternating eastward and westward jets, similar to Jupiter's, but with different structures and speeds. Equatorial jet reaches 1,800 kilometers per hour, making it the fastest sustained wind in the solar system. At Saturn's north pole sits a hexagonal storm that has been continuously observed since Voyager first photographed it in the early 1980s. The hexagon is a standing wave in the jet stream, a stable geometric pattern in atmospheric flow, with each side approximately 13,800 kilometers long, wider than the diameter of Earth. Its interior rotates at a different speed from the surrounding atmosphere, and faint at its center sits a hurricane-like vortex with an eye 50 times wider than the average Atlantic hurricane. The hexagon's color changes with the seasons. When Cassini arrived, the North Pole was in winter, and the hexagon appeared blue, colored by the scattering of light in an atmosphere not yet illuminated by direct sunlight. By 2016, Saturn's North Pole had moved into summer, and the hexagon had turned gold, as sunlight drove new photochemical reactions in the upper atmosphere. Cassini watched a polar season change on another planet in real time. Saturn also emits significantly more heat than it receives from the Sun, approximately 1.78 times as much. This excess energy comes from the slow gravitational settling of helium droplets through Saturn's interior, a process called helium rain. As the planet cools over geological time, helium condenses out of the hydrogen-helium mixture in the deep interior and falls toward the core, releasing gravitational potential energy as heat. This process is theoretical, proposed decades ago to explain Saturn's excess heat, but the precise rate of energy output that Cassini measured has allowed planetary scientists to constrain models of Saturn's internal structure and evolution with a precision not previously possible. Saturn's rings are arguably the most recognizable structure in the entire solar system. For centuries, they were viewed as ancient, permanent features that had existed since the birth of the planets themselves. Cassini changed that understanding completely. Over 13 years in orbit around Saturn, the spacecraft studied the rings in extraordinary detail, and what it discovered was deeply surprising. Evidence gathered during the mission suggested the rings may not be primordial at all. Instead, they appear to be relatively young on cosmic timescales. By analyzing subtle gravitational interactions between the rings and Saturn's interior, scientists were able to use the rings almost like a giant planetary seismograph. Tiny oscillations inside Saturn created detectable patterns within the ring system itself. The data pointed toward an astonishing possibility. Saturn's rings may only be between 10 and 100 million years old. That sounds ancient by human standards. But compared to the solar system's age of 4.6 billion years, it means the rings could have formed relatively recently, possibly around the same era dinosaurs still walked the Earth. Cassini also revealed just how physically strange the rings truly are. The main ring system stretches roughly 282,000 kilometers across from inner edge to outer edge, an enormous distance spanning most of the gap between Earth and the Moon. Yet despite that immense width, the rings are incredibly thin. In many places, they measure less than 100 meters thick. Some regions are only around 10 meters deep, astonishingly delicate for structures visible across billions of kilometers of space. To study them, Cassini performed radio occultation experiments, sending radio signals through the rings toward Earth. By analyzing how those signals changed while passing through the icy material, scientists could map particle sizes, densities, and structures hidden within the rings themselves. What emerged was not a set of smooth, uniform bands, but a dynamic and constantly changing system filled with waves, gaps, clumps, and intricate gravitational interactions. And some of the mission's most important discoveries came during its final chapter. In 2017, Cassini entered a phase known as the Grand Finale, a series of daring orbital maneuvers unlike anything attempted before. Using Titan's gravity to reshape its trajectory, the spacecraft began diving repeatedly through the narrow gap between Saturn's innermost ring and the cloud tops below, a region only about 2,000 kilometers wide. Over the course of 4 months, Cassini completed 22 of these passes. For the first time in history, a spacecraft directly sampled material from Saturn's rings while simultaneously studying the upper atmosphere of the planet itself. These close approaches allowed scientists to precisely measure the mass of the ring system and observe something unexpected. The rings are slowly disappearing. Tiny particles of ice and dust are constantly being pulled by Saturn's gravity into the atmosphere below in a process known as ring rain. Over immense spans of time, this steady loss of material will gradually erode the rings away. At the current rate, Saturn's iconic rings may largely vanish within the next few hundred million years. Future civilizations, if any ever exist, could see a Saturn that looks dramatically different from the one humanity knows today. But by the final year of the mission, Cassini itself was nearing the end. After nearly 2 decades in space, its fuel reserves were critically low, and without fuel, the spacecraft would eventually lose the ability to stabilize and orient itself correctly. An uncontrolled Cassini posed a serious problem. Because of discoveries made at moons like Enceladus, NASA could not risk the spacecraft accidentally crashing into a potentially habitable environment. Even microscopic Earth organisms surviving on board could contaminate world scientists now considered biologically important. So the mission team made a deliberate decision. Cassini would end on purpose, and if the spacecraft had to die, it would do so while gathering as much scientific information as possible. The grand finale officially began on April 22, 2017, after a close flyby of Titan altered Cassini's orbit one final time. From then onward, the spacecraft repeatedly plunged between Saturn and its rings, collecting unprecedented measurements of the planet's gravity, atmosphere, and internal structure. It sampled atmospheric gases directly. It photographed Saturn's cloud tops from distances no previous mission had ever achieved. It helped scientists better constrain the size and composition of Saturn's core. Then came the final flyby. On September 14, 2017, Cassini passed Titan one last time in what mission engineers emotionally referred to as the goodbye kiss. Titan's gravity gently adjusted the spacecraft's path for the final time, locking it into an irreversible descent towards Saturn. There was no turning back. Less than 24 hours later, Cassini entered Saturn's atmosphere. As it fell, the spacecraft continued transmitting data continuously back to Earth, measuring atmospheric temperature, pressure, and composition in a region no probe had ever explored directly before. Its thrusters fired constantly, fighting to keep the antenna pointed toward Earth for as long as possible. But eventually, the atmosphere became too dense. Cassini lost stability. The spacecraft began tumbling uncontrollably as aerodynamic forces overwhelmed it. Then the signal vanished. 83 minutes later, after crossing nearly 1.5 billion kilometers at the speed of light, the final transmission arrived on Earth at 7:55, 46 seconds in the morning Eastern Time. Cassini was gone. After 20 years in space, the spacecraft that transformed our understanding of Saturn and its moons no longer existed. It had become part of the planet it came to explore. Cassini's true legacy is not contained in one single discovery. Its achievement was far larger than that. The mission fundamentally transformed humanity's understanding of the Saturn system itself. Before Cassini arrived, Saturn was largely viewed as a beautiful but relatively predictable world. a giant gas planet surrounded by spectacular rings and frozen moons thought to be mostly inactive and lifeless. After 13 years of exploration, that picture no longer exists. Cassini revealed a planetary system far more dynamic, complex, and scientifically important than anyone imagined. It uncovered a moon hiding a global ocean with conditions potentially suitable for life. It exposed another moon with rivers, lakes, rainfall, and seasonal cycles eerily similar to Earth's, despite being hundreds of millions of kilometers farther from the Sun. It showed that Saturn's rings are not ancient relics from the formation of the solar system, but comparatively young structures slowly eroding away over time. Even Saturn itself became more understandable through Cassini's observations. By studying tiny disturbances and wave patterns inside the rings, scientists were able to detect oscillations deep within the planet's interior, effectively using the rings to study Saturn from the inside out. And despite the mission ending in 2017, researchers are still analyzing the enormous amount of information Cassini returned to Earth. Its discoveries continue shaping the future of planetary science. Perhaps nowhere is that more obvious than with Enceladus. Before Cassini, the idea of searching for life inside hidden oceans beneath icy moons was still considered speculative. After Cassini directly sampled material erupting from Enceladus into space, that concept became one of the central goals of modern planetary exploration. Missions being developed today were heavily influenced by what Cassini found. NASA's Europa Clipper mission, now traveling toward Jupiter, was designed in part around the same scientific strategy pioneered at Enceladus, studying material venting from subsurface oceans without needing to drill through kilometers of ice. Meanwhile, both NASA and the European Space Agency continue discussing future missions specifically focused on Enceladus itself. Spacecraft capable of repeatedly flying through the plumes and searching directly for biosignatures, the chemical fingerprints associated with life. Cassini made those missions scientifically unavoidable, because after what it discovered, ignoring Enceladus is no longer an option. And there is something strangely poetic about the way the mission ended. A spacecraft sent to study Saturn eventually uncovered worlds so scientifically valuable that NASA chose to destroy it rather than risk contaminating them. Then, in its final moments, Cassini continued transmitting information while falling directly into Saturn's atmosphere, still conducting science until the very last second. And throughout the entire mission, that pattern repeated itself again and again. Cassini consistently found more than anyone expected. It arrived to study Saturn's weather and discovered an ocean world that may be capable of supporting life. It explored Titan, expecting a frozen moon, and instead found rivers, lakes, rainstorms, and seasonal cycles operating in alien chemistry. It investigated Saturn's rings and learned they may be young enough to have formed while dinosaurs still existed on Earth. Cassini did not uncover alien civilizations. It did not detect hidden signals or impossible technologies. What it found was something arguably more profound. It found that the ingredients and environments associated with life may be common in places humanity once assumed were sterile and dead. And perhaps that is the most important lesson the mission left behind. The universe does not need exaggeration to be extraordinary. The real cosmos is already far stranger, more beautiful, and more mysterious than science fiction ever needed to invent. Thanks for watching. See you in the next one.